Continuing on, we have a track star running around an oval track at constant speed. At which point or points is his centripetal acceleration the greatest? So, oval track, I'll call this point A, this point B. And, this point and this point would be the same, this point and this point would be the same. Now, most people correctly say that it's one of these 2 points, A or B. If we remember, centripetal acceleration is v squared over r, right? The speed is constant, so the radius is what determines which acceleration is greater. But people often incorrectly interpret this radius. What this radius means is the radius of curvature. So it's not the distance to the center of this oval. It's the distance to the center of the portion of a circular path they're on. So here we're curving more tightly. So this is kind of the circular path we're on, this little circle. So the radius of curvature there is pretty small. Whereas here, you've got this big old circle that would be the curvature at that point. So this is a much larger radius. So point A has a smaller radius, and if you decrease the denominator, you get a bigger value over here. So point A has the greatest centripetal acceleration because it has the smallest radius of curvature. Now this next question seems to be, it kind of winds up seeming the opposite of this, and I'll explain why that is. So 2 masses are attached to a string. One is at the end of the string, one's halfway down. Whirl it around in a circle. What's the acceleration of the other one? So mass attached to a string, and then we go around in a circle. So if you think about this formula, think, okay, radius. This one has a smaller radius, right? So it has a bigger centripetal acceleration. But then we forget velocity. Well, which one's covering more distance? They both would cover, in one rotation, they would both cover 360 degrees, but this one has more distance then, so which one's bigger? Well, in this case, it's better to consider the other version of the centripetal acceleration formula, because what they share in common is the period. They're both going to take the same amount of time to go in a full circle. So the period's the same, and then we look and see, okay, when the period is the same, acceleration is proportional to radius. So one has an acceleration A subscript c. The other one, the radius is half as big, so the centripetal acceleration, so we divide radius in half, that means the other one has a centripetal acceleration that is half of the one in the middle is a centripetal acceleration that is half of the one on the outside. This one is a similar question. Circular track moving at constant speed. They're going around the same track. They have different speeds. We can just look at the formula. Centripetal acceleration equals v squared over r. So centripetal acceleration of A is v squared over r. Centripetal acceleration of B is equal to 2v squared over r. So what's the ratio of B's acceleration to A? So B is 4 times as big as A, so the ratio of B to A is 4 to 1. Okay, so doubling velocity quadruples the centripetal acceleration. Number 5 here is just a simple plug and chug, although it's a little bit complicated. We got 4 laps in 25 minutes, 1 kilometer track. So we know centripetal acceleration equals v squared over r. So what's our velocity? Well, 4 laps, 25 minutes. Okay. 4 laps. 4 laps is 4 kilometers. which is 4,000 meters, and the time is 25 minutes, which is 25 times 60 seconds. So if we take 4,000 divided by 25 times 60, we get that our velocity is 2.6 repeating meters per second. I will store that value as v. Now what's the radius of my track? Well, 1 kilometer is all the way around the outside, so 2 pi r equals 1 kilometer. So my radius is 1,000 over 2 pi. And now we've got our values. We can calculate centripetal acceleration. 2.6 repeating squared over 1,000 over 2 pi. So we take that value squared divided by 1,000 over 2 pi. We get a centripetal acceleration of 0.0447 meters per second squared. Pretty simple calculation, just a little bit of conniving you have to do with that 4 laps in 25 minutes. There's another example. It's a little bit trickier. Got a car traveling around a bend in the road with a radius of curvature. The car just barely avoids skidding. So just barely avoids skidding. That means we can look at that and say, okay, we've got the maximum value of static friction. Right. Now, I didn't state this. I should have stated that the road is flat. Now, if the road is flat, looking back, we talked about this, road being flat, the only thing that's contributing to the centripetal acceleration is static friction. So when we can write Newton's second law. The sum of the forces is the maximum value of static friction, US times normal force, and our acceleration is centripetal acceleration, mv squared over r. In this case, in the vertical direction, the only forces acting are normal and gravitational, and the car is not accelerating in the vertical direction, so we know that normal is equal to mg, and then we can calculate, mass cancels out, and we can calculate the coefficient of static friction. It's equal to v squared over gr, which is 12 squared over 9.8 times 45, which we can get a number for. And it's about 0.327, not very good. Actually, good tires on a road will get you a coefficient of friction of about 1.6. Maybe the road's a little wet or something, I don't know.